Hello everyone, my name is Narina Kokhlikyan. I'm a research scientist at Facebook, and this talk is about model interpretability. This talk is structured as follows. I'll start with a brief introduction of model interpretability and recap CapDoom library that we introduced during previous PyTorch developer conference. Then I'll talk about the extensions of the library that we made during recent 2 releases. After that, I'll walk you through the collaborations and external contributors and the future directions that we are taking for the library. The definition of model interpretability is rather elusive, but for the sake of clarity, let's define it as the ability to describe AI model internals and their predictions in human understandable terms. You might wonder, why is model interpretability important? Why do we care about it? It is important because it helps us to understand how our models reason. It helps us to debug misclassified predictions and understand how we can change our models to also improve the model performance and our prediction quality. For those reasons, we developed a library called CapDoom. As I mentioned, we introduced CapDoom during a previous PyTorch developer conference, but I'll recap the library before we dive deeper into the new features and algorithms. One of the important characteristics of the library is multimodality. This means that we can use the library for any type of PyTorch model and features. This can be text input features, or image, audio, video, any type of dense or sparse features. Secondly, the library is extensible. We can add new algorithms and new features. And thirdly, it is designed for easy use, so we can use it with a couple lines of code. We also have a preprint version of the paper that describes CapDoom library in case you decide to use our library and cite the work. So the first release that we had last year contained a number of gradient-based attribution algorithms that allow us to interpret output predictions with respect to the input, output predictions with respect to all neurons in a hidden layer, and neurons with respect to the inputs. To do that, we came up with a generic formulation of attribution definition that will help us to generalize across various types of attribution variants. For that, we can define an instance of attribution algorithm by using the forward function of our model and call attribute on that instance by passing the input features for which we would like to compute the attributions. Here is an example of primary attribution or feature importance, where we attribute the output prediction target 0 to the input features of our model. On the right side, we can see how we can do that using integrated gradients algorithm, and we see how we use the same generic signature of attributions to compute feature importance. The same philosophy is valid also for neuron attribution. In this case, we select an internal neuron and attribute to input features. On the right side, we can see that we chose a neuron gradient sharp algorithm, and we call attribute on the algorithm by passing our model, inputs, and also the neuron index. The same definition is also valid for layer attribution. In this case, we attribute the output target prediction to a hidden layer. On the right side, we can see example code that computes layer attribution using layer conductance. So this was what we had in the first release. Now, in the second release, we added a number of perturbation-based attribution algorithms. So these algorithms also have the same signature, same generalized definition of attribution computations that we had for gradient-based approaches. Apart from that, we also added new variants for the layer and neuron attribution algorithms, both for perturbation and gradient-based approaches. We had also a number of bug fixes and improvements in the library, and the library also got used in a number of research and production projects. This diagram summarizes all algorithms that we had in the second release of the library. On the left side, we can see the list of algorithms that allow us to attribute output predictions and internal neurons to the inputs of the model. On the right side, we can see the list of the algorithms that allow us to attribute output predictions to internal hidden layers. Gradient-based approaches are highlighted in purple, perturbation ones in pink, and the other two approaches that do not belong to any of those two groups are highlighted in dark blue. Some of these approaches are baseline simple approaches, such as silency layer activations. These approaches we also had in our first release. On this slide, we can see all the approaches, highlighted all the approaches that we added in the second release. So as we see, this includes a number of perturbation-based approaches such as occlusion, Shapley value sampling, feature ablation, feature permutation, and also layer variants for different types of algorithms. We can see that within these algorithms, there are a couple of them that are stemming from computer vision community. So these algorithms include guided GradCam, occlusion, deconvolution. Although these algorithms are originally coming from a computer vision community, our implementations are generic, and they can also be theoretically used for any other types of models. Now let's look what we offer in our third release of the library. So in the third release of the library, we expanded the list of perturbation-based attribution algorithms and added LAM and kernel SHAP. Besides that, we also initiated Captum.metrics package and added two evaluation metrics called infidelity and maximum sensitivity. These two approaches allow us to evaluate the goodness of attribution algorithms. Maximum sensitivity measures the sensitivity of explanation to saddle input perturbations using Monte Carlo sampling-based approximation. On the right side, we can see how we can import sensitivity max from the Captum.metrics package. For this, we also need an explanation function, and in this case, the attribution function itself is a special case of explanation function, which we can use from our Captum.attr package, as well as we need to define the inputs for which we want to compute the explanation and a perturbation function. We also offer default perturbation functions that the user can use. The second evaluation metric is called infidelity. Infidelity measures mean squared error between dot product of input perturbations and explanations and the difference between the predictor function at its input and perturbed input. This metric is the generalization of the completeness axiom that we already know for a number of attribution algorithms such as integrated gradients and the deep lift. On the right side, we can see how we can use infidelity function. For that, we need a forward function of our model, a perturbation function, the inputs for which we would like to compute the attributions, and of course, the attributions. So the attributions can be computed using Captum algorithms from Captum.attr package, or we can also use any other external packages to compute the attributions if we prefer to do so. Let's talk about the collaborators. We had a number of collaborators, and I would like to mention a couple of them. One of them is Fiddler. Fiddler is an explainable AI company which incorporated Captum into its platform and offers as a solution to its users. Now, Fiddler users can use Captum to explain their PyTorch models. Another collaboration we had with OpenAI, which resulted in a Captum.optim package that offers optimization-based visualizations. This is an ongoing effort, and we also have a number of new external contributors that are working on shaping this package. Besides that, we also have a layer-wise relevance propagation as an ongoing contribution and efficient silencing methods such as FastCam. We have a number of future plans to extend Captum library. This includes support for concept-based model interpretability, adversarial robustness that will allow us to estimate the sensitivity of our models and the explanations to various different black box and white box attacks. Captum.optim for optimization-based visualizations, and expansion of the metrics package that will allow us to estimate the trustworthiness of the predictions and explanations. Besides that, we have also a plan to offer tools for debugging and monitoring PyTorch models and various different types of embedding visualization tools. So to recap, I talked about 3 releases of Captum library that we had and the attribution algorithms that we currently offer, and the 2 metrics, infidelity and maximum sensitivity. I'd like to invite you to check out our website, captum.ai, and our GitHub page, github.com/pytorch/captum. Please make contributions and also report issues if you see any. And of course, also, I talked about the future directions that we are taking for the library with respect to concept-based interpretability, adversarial robustness, optimization-based visualizations, and embedding visualizations. This is all. Thank you very much for watching our talk.